Yeah, welcome to this new edition of a lecture about high-dimensional fields, how they move us toward accounting for higher cognitive function in dynamical field theory. So the first part of the course really introduces to the core elements of dynamical field theory, understanding that the field dynamics combine input, for instance, here's some localized input, into a field with strong interactions, so local excitatory and global inhibitory interaction that leads to the emergence of stable peaks that represent units of representation or are units of representation. And they enable selection. For instance, here, if you two local inputs, you can select one of those two. They enable detection, the creation of peaks, and a form of working memory in which peaks may persist once the input set has been removed. So you're all very familiar with, and all of that we looked at in the simple case of a single dimension X, and we talked about how these dimensions may come about from the connection to the sensory surface or to the motor surface and so on. So today I'll start talking about more than one dimension, multiple dimensions. And my first point is going to be there's nothing special about that, but then we'll see that actually new cognitive functions may emerge from that. So first, let's make sure that you see that there is nothing special, that it's a straightforward generalization. I already showed you examples of two-dimensional fields estimated from neural data. This was this work using the distribution of population activation, where the space that was represented was two-dimensional, was the retinal space, right? This was the white square here scans out a certain part of the retinal space where the phobia was here on the left, and a particular stimulus was brought up in different locations in space. And then we were able, with the techniques that we looked at there, to estimate the neural representation of two-dimensional retinal space using the combination, these techniques of using the tuning curves, receptive field profiles to construct a population representation. And that obviously is two-dimensional. And actually, Dirk Janke, who did this work a long time ago, generalized that to a two-dimensional representation that represents different kinds of dimensions. So here he probed orientation as a dimension by looking at orientation tuning curves and sampled the visual space, the retinal space, just along one dimension. And so these, for instance, are representations of orientation combined with location. So a two-dimensional field of a different kind. This is when you do that more completely. This is actually observing orientation feature maps on the cortical surface. So the different colors here indicate different preferred orientations of neurons in different parts here on the cortical surface. And they are also actually representing the two-dimensional visual space. So you can see that if you have three parameters that you want to represent, orientation and the two-dimensional visual space, then you can't actually map that in a two-dimensional cortical sheet, and you have to use these techniques of constructing population representations of sort that, to combine all the different, the neurons stand for different orientations and different space, and sort it out in a three-dimensional representation. So that's possible. So here there would be examples of doing that. Here, for instance, this would be an example of a three-dimensional field where two dimensions are retinal space and the third is orientation. That could be obtained by sorting these feature maps, in terms of these underlying dimensions in a population representation. So here these simulations that are running, just to remind you that the fields of these various dimensions work similar to the one-dimensional field. They can do selection, they can make detection, and can have all the instability. So there's nothing special about scaling in that way. In three dimensions, peaks are little blobs in 3D. These are three-dimensional fields. We'll see that later. You can do this in 4 dimensions as well. There is mathematically what happens is if you increase the number of dimensions, you can have sometimes new attractor solutions that may arise, for instance, rings of activation, but they don't necessarily arise. You can create conditions where they don't arise. So as such, there is nothing special about high dimensions somehow changing the dynamics. but we'll come to some issues a little later. I should mention that we're also often talking about nodes, neurodynamic nodes, which we used to call zero-dimensional fields. In fact, in the book chapters that are online, you will see that kind of language. That's a little bit misleading because, what does that really mean? It's sort of discrete neural activation variables. In many cases, they are really embedded in some kind of ensemble where they all inhibit each other. So you're making selection decisions and detection decisions. You might also have working memory for discrete neural nodes that all compete with each other. So they are, in some sense, sampling a field, but it isn't really spanned by continuous dimensions. So it's very appropriate to present, for instance, concepts or categories. And the sort of the output layer of a categorizer could be viewed that way. And that's how we use that. I'm not sure I will have a chance to present that kind of work in this lecture course. We're doing work like that. So, for instance, a lot of our work, these discrete nodes then become to stand for something specific. For instance, you could have a node that stands for blue, and it stands for blue in the sense that it has some synaptic connectivity to a particular region on a color field, a field that represents color. So, for instance, over the blue, by having that synaptic connection, you could induce a peak from the projection from this node to create a blue peak. And vice versa, you could categorize, color input, if you have a peak like this, to activate the concept node, the blue concept node. That's just one way we use two-dimensional fields. They have the same kind of dynamics, and you played with that, right, in the discrete neurodynamic simulator. We also sometimes use discrete nodes that stand by themselves, that are not embedded in a field of neurons that they compete with or nodes they compete with. So, for instance, the common use of that is what we call a boost node. So there are some occasions when a neural node will potentially activate an entire field homogeneously. And when it becomes activated, it will sort of lift activation in that field and enable, therefore, for instance, peak generation if there was some slow subfield, sub-threshold activation pattern. This is what I illustrated when I showed you this simulator, and you had an exercise about that when you apply the boost, and the boost would then not come from some slide in some program, but from a neurodynamic node that becomes activated and then makes that boost. So nodes play a special role and are actually an extension of our concepts, and we'll talk about that, of our dynamic field concepts. We'll talk about that in the new year. So that's just the dynamics of fields. Now let's look at what it actually means to have these multiple dimensions. And again, it would not actually be special if it's just 1, 2, or 3 dimensions of space. If it's interesting if it's different dimensions. We already talked about that when I reviewed briefly the classical Hubble-Wiesel work. I mentioned that the neurons in primary visual cortex seem to respond specifically to both the spatial location of a stimulus, as marked out by the receptive field, these dashed lines here, as well as a stimulus parameter, or a feature parameter, like the movement, the orientation of a moving bar, which is here combined with the movement direction of the moving bar. So you could say the neurons, in a way, encode both of these things, this two-dimensional space plus at least this one parameter, the directional tuning, maybe multiple parameters. So in that sense, they represent the combination of these parameters. One could talk about binding these parameters together, binding it anatomically in the sense that, well, one neuron represents one particular combination. If I think about, where this orientation lies, that's the particular value this neuron represents, and then the center of its receptive field, that's the spatial location it represents. And other neurons would represent other particular combinations of values. So that makes sense if you're going to think about the whole field as combining feature dimensions this way. So here's an instance of a field defined over color and visual space. I just take one visual dimension to make it easy to illustrate. It will be more typically a 3-dimensional field, the nature I just showed earlier. So if you have a visual scene in which colored objects are different locations, then that scene might provide input to a field like that. So, for instance, that this object here would create a peak at the location that, spatial location and the location that encodes the color seen here, like green, and that object induces peak at this location on the retina and maybe this color, right? So in a sense, this field represents the bound representation, or is a bound representation of these two different dimensions, color versus space. And once you have that, I was arguing just previously that this is natural. This arises in the visual cortex, for instance, because you have forward projections that extract features and represent combinations of feature values this way. So once you have that, you can actually do a couple of operations on these fields that may become useful to do cognitive processing. The simplest one is to just extract the bound values. So for instance, if you have this field and you project out by summing along all spatial locations for any given color, you can just extract the one-dimensional information about color. When you sum, you might take maybe a sigmoid, or you could take a softmax. There are different ways to do that. But you can just think of that as summing all suprathreshold activation, and that provides input to a one-dimensional field. So you're extracting the color dimension, and you could similarly extract the spatial dimension. That will be extracting the individual values. And then you could conversely combine values that you actually have not bound. So for instance, if you know the color of an object, you could boost all the neurons that represents combinations of color and space consistent with that color. There will be a ridge of input. So that's what you would do. You wire this up so that it excites all the neurons that are along this line. And similarly, if you know something about space, you could activate the ridge of all of these combinations. And if you combine these two things, you can bind the two pieces of information by creating conditions under which a peak forms where these ridge inputs overlap. There will be more input there, and you can make sure that detection occurs exactly only at levels where they correspond to at least two of those inputs, and you would not get a peak anywhere else. So this is now a bound representation of that particular color in that particular spatial location. And we'll see that this technique can be used in cognitive processing. This is where the first instance where the binding problem arises, because you immediately see that you can't really combine feature values of more than one, I'm saying object now, more than one local maximum at a time. So here, this is the color representation of the original visual scene that I showed you with the two objects, and this is the spatial representation. And if you were trying to bind these two, you see that you would get these ridges, and they overlap or intersect at 4 locations, because you don't know if the green is at that location or this location, and the blue or this or that. So actually combining feature values to bind them actively only works if you do it one object at a time. Once you do that for more than one object, you have this problem, this so-called illusory conjunction. Actually, there are experiments that hint at problems like this. I was talking about objects, which is actually appropriate, because here it's really the location that allows us to tell apart different combined values. And that's actually a very general theme that visual space plays an important role in resolving issues like that. And we'll see that a little later in this lecture. So this so-called binding problem actually does play a role, and you'll see that over the course of this lecture. It creates some kind of sequentiality bottleneck, and we have a lot of cognitive functions that have to do with visual cognition. We're talking about objects in the world in which the need to sequentially operate on individual objects, which I'm saying now, which really means typical visual location, is necessary. And the cause for that is ultimately this kind of problem. Visual search, or more generally search, is a combination of these two kinds of processes. So in visual search, what you have is that you actually have a bound representation for your visual scene, and you have the 2D entries here. And now you want to select within that bound representation a particular object and extract its feature. maybe its location, for instance. And one way to do that is to say, I'll provide that ridge input that we use to bind, and we arrange that only the peak that overlaps with that ridge is above the detection instability, and this peak is below. And then this will be the only peak that forms. And if you project that out to the spatial field, you can read out where the object that has the color that you encoded into this field lies. So that will be visual search, looking for an entry into this high-dimensional database, if you want, that matches a particular search pattern here, a particular color value. And in fact, that is literally the account given in DFT to the psychological phenomenon of visual search. We have a whole line of work. We published a rather extensive and complex model. I hope this wasn't on the video. My simulator just finished a run and claimed the screen. I'll just sketch that model. That is a model that Raoul Grieben does in my lab, who's in the last days or weeks of his PhD. So here is, this is a survey of the model. Maybe let me go through some components. So the visual scene that we do visual search on consists of simple objects. This is the kind of scenes that are shown to you. Participants in visual search psychophysics experiments, and they have a task like looking for the diagonal green one, or actually the search. I don't actually know exactly what the search item was here. And you see that there are different colors here, different orientations, and certain kinds of shapes, which we are called here templates, these sort of wiggly shapes versus these more oval and the more rectangular shapes. And this input is for the model is given into a forward feature network for forward projection that extracts color representation. So actually here, just in terms of hue over the retinal location, it extracts orientation by applying certain filters, and that are essentially synaptic patterns. It applies that to the saturation of the color. So that's like the intensity variable for color. And then it does some form of template matching to extract how strongly these different shapes are represented. And that's a shape versus space representation. And that is fed into what we call scene feature maps. That is, there are three features here: the color, orientation, and shape. And these features are always defined over retinal space, on the image space. So it's three-dimensional fields, three-dimensional fields. From which you can extract something we call a conspicuous map, and ultimately a seance map, where you're essentially integrating over the feature dimensions and just registering where there is significant activation in any of these feature fields. And that will have some influence on selecting an item, which means a local location. Now, the guidance occurs through a representation of the search queue. So, for instance, if you tell the system to look for certain color, certain orientation, certain shape, that will provide ridges in 3D. A ridge is a slice, and that slice will then enable peaks to form where 3D input overlaps with these slices. The input comes here from this column we just looked at. And then you would be summing across these different fields in a particular way that takes into account how many of these cues are present. And that purely spatial information will then be combined with the seance input to make a decision, a spatial selection decision, that then brings an item into the foreground. And once you have an item in the foreground, you're going to look at whether it really matches the cue. And that's something, I'm not going to go into detail, but that's something that happens because the human psychophysics tells us that people are actually tuning these maps to allow objects to be selected that don't match on all dimensions, that actually typically match on at n-1. So if you have n dimensions, n-1 matches are enough to be selected for attention. And so every item has then to be examined for whether it actually really matches on all dimensions. And if it doesn't, it's actually inhibited in this map, and you're allowing the next item to come up. And this serial selection of objects, which reflects, again, the perceptual bottleneck, the attentional bottleneck, that you're looking at one object at a time and then checking for its validity, that is actually the key signature of visual search. Visual search data all consist of saying the time it takes to find its target depends on how many distractor items are in the display that are like the target, except for one dimension where they differ. If they differ more than one dimension, then they are not actually selected, and they don't prolong that reaction time to the visual search. So that's the sort of data this whole fields always deals with. In this model, it does that and accounted for these kind of effects. Here's just a simulation from the model. You see, actually, this is how the search queue is given. We're just inserting it. This is actually a camera image. We're sorting this item, and you actually see that now this item was selected attentionally because there's a change detector, transient detector in the model, and it will now look for an object that has this matching color and that has this this orientation. It actually first selects this object here at the bottom because it's very salient. There's a lot of input, but then finds that it doesn't really match when it does this detailed matching, and then ultimately it finds the right object here, the matching object, right? This one. And there's more to this than I can explain here, but that so one important point that is an outlook for the future is that you see these different events happening, something coming up and so on. That is actually all done autonomously by this big neurodynamics, sequential processing, and we'll be talking about that in the new year, how sequences of processing steps arise autonomously from dynamic field theory. That's sort of a central insight in the book. It's like the last chapter. You can see it's a bit advanced, but it's actually a very important constraint for how we build dynamic field theory. Good. So that's visual search. That's already a higher cognitive function, very important function. In fact, it generalizes to search in a broader sense, in that you can think of if you search in your mind for like the next word to say or the next point to make, you could think of a very similar kind of mechanism where you're just boosting those things that are perhaps reasonable to now activate, and you have to have some mechanism of how to sequentially do that, and that's what we'll be talking about later. But the core idea is the same. Is the idea of biased competition, as this also called, that you pre-activate the candidates and then you select the ones with most activation. Now, this binding that I threw out there is actually also a real cognitive function, and I want to do one step of going beyond the very simple anatomical binding that that the high-dimensional fields per se achieve. And I'll talk about binding through space and use that to talk about localist versus distributed representation. And not really talk about learning. I don't know. We can do that maybe in the discussion session. And so let's first look at a scaling problem. Now, it's kind of obvious that if you combine many different feature values by always adding a dimension, then that's very costly because you need a lot of neuron, a whole sampling of the space, every combination, that goes like the power of the number of dimensions. So just to give a concrete example, if you had two spatial dimensions and you have these feature values that I just arbitrarily picked here, like depth and orientation and color and texture, which would be maybe spatial frequency, maybe movement direction and size. And I took as an example that you have 8 dimensions to represent, and you need 200 neurons per dimension, just a number. It's not very large, right? Then you would have 10 to the power of 16 neurons to represent that, all the combinations of all these different values, right? So that is more than there are neurons in the brain. So see, there's a problem with scaling that. And we know psychophysically that we represent actually more than just 8 dimensions about visual objects, and very similar things about auditory objects and so on. So that means that this anatomical binding doesn't scale. We can only bind, in that sense, a small number of dimensions. So what's the alternative, or what's the problem? So one thing is to be aware that this problem comes from the fact that we're using localist representations. And localist representation, meaning these peaks, that is a particular location in the space that we're reconstructing to represent something for a featured dimension. That these localized peaks represent information, and that ultimately comes from or is associated with this localized local excitatory global integer interaction kernel, which makes that you can create these peaks and sustain these peaks and make selections among the peaks, and that does all our machinery, right? But you could also think of that as a very costly way of representing things. And I mentioned that earlier, that a much less costly way would be to say, well, if I have to represent a spatial location, I just introduce one neuron for X, one neuron for Y, and the rate of neuron X and the rate of neuron Y, that would be the combination of all possible values. So that's much more efficient. And so that's going away from positional encoding, and the more general term from that is distributed representations, or representations where it's the activation pattern that are distributed across neurons. That is, different neurons contribute to different representations, and it's just a pattern that decides, and which is very commonly assumed in connectionism and deep learning. Those scale much better. They can represent a lot of different dimensions in a sense. But these localist representations, they do not, actually, there's a not missing. Actually, sorry, this text at the bottom I should have deleted because I think I have a separate slide for that. No, so let's just say the localist representations are useful still, even though they're costly, because they enable the peaks and the detection, selection, and sequence generation, and so on. And so in DFT we stick to that because that is critical for our function. Sorry, I got confused here for a moment. This but is a but against saying that they don't scale so well, these localist representations, but they have that advantage. The best known alternative to that are Hotfeed networks. I alluded to them earlier. Here's an illustration from a review paper by someone called Rolls. In the Hotfeed network, every neuron is connected to every other neuron. Here in this particular picture, it makes a synapse here on all the other neurons. There are only 4 neurons here. That neuron makes a synapse on all other neurons, and so on. They can also get an input, and then you can look at the activation pattern as an output. And because of that recurrent connectivity, these networks can also be shown to create stable states, attractor states. But these attractor states, are specific to the connectivity pattern. That is, there are only certain patterns that are encoded in this interaction pattern. And Hotfeed and his collaborators computed how many of these attractors you can create in a particular, given a certain size of the neural network. So these are actually proposed as models of memory, in the sense that specific patterns, right? You have, if you have learned all these synaptic strengths, then you have a specific activation pattern that you can recreate in the absence of complete sensory information. But they're not good candidates for the general purpose cognitive representations that you do your operations on, that you have working memory for, or that you can make selections on, or that you can create sequences, which I haven't explained yet fully. So that's why we are not going for this. And in fact, I'm not aware of anyone trying or successfully achieving cognitive function from these networks, except for memory, long-term memory. Okay, so we do have that scaling problem. So how can we solve it? Well, it has been a proposal in the literature for 30 years, going back to a psychophysicist called Anne Treisman, who died of just 2 or 3 years ago. But so this work was like in the 60s, 70s, I believe. And there's a lot of people who contributed to that. And they had a notion that was sort of a verbal theory. It wasn't really neurally specific. That one could have separate representations of different features. For instance, as an example, size and orientation and color separate. And but that means for us, separate neurally, different neural populations. And if they all just share one dimension, or one set of dimensions, and that will be in Treisman's proposal visual space. So here they all have a represented visual space. Then one could effectively bind these different things. And the original theory was some kind of information processing theory where there would be an object file being created and like stored in memory and so on. It wasn't really neural, but we're actually now interpreting and providing process models for a neural realization of that. And that's based on the fact that in our fields, we can actually create instances. So in that sense, store something in working memory. We don't have to write a file for that, right? It's an emergent property of neurodynamics. And I just illustrate in the next couple of slides how that works. So here's a survey from that model that I quoted earlier, actually uses binding through space. So essentially the idea is if you know the spatial location of an object, and you know its feature values in some way, you can create the bound version of that by just making a column input at the right spatial location and a slice input in 3D at the feature location. And where these things intersect, that's where we'll create peaks. And so these 3 peaks can be created at the same time and are connected through spatial location. And here, I'll give you here sort of an academic example to show how that works in principle, and I'll show you a more realistic example. Let's say if you have color and some kind of shape representation of the letters and one-dimensional retinal space, just to make it simple. Then you let's say that's your input, and you want to know what letter is the what shape do you have that's green? And so here these different entries are the entries from the stimulus array. So the different colors here of these inputs and the different shapes of these inputs. And the way you would answer that question is that you would give the visual cue to green by putting a ridge into that. And so the only peak that overlaps with green would correspond to this spatial location, and that would project into a spatial representation, which then conversely could be used to now boost through this boost this spatial location, and at that spatial location in the other fields only one object overlaps with that spatial location. That's the object that shares the spatial location, and then the peak that forms here can be read out, and you can read out the shape. Once you've read it out, there is actually a peak here, and that peak will make that there's also a ridge along this dimension, and that makes that looks here like these ridges in both of these fields, because now you have the 2 feature values that are associated through space. Now that's how you get from one dimension to the other through space. So you're using space to associate these 2 locations. Here's a model of visual working memory that is actually the way that all of these binding experiments from Treisman labs and many other labs have worked. It's typically a situation where you have a visual scene, and you have to, and then it's shown you for a while, and then sometime later you're going to be presented with a different visual scene. You have to say, is it different or the same as you saw? And it might differ along one feature dimension. One item might differ, and that item might differ along one feature dimension. The critical thing is you could actually create conditions where it still has the same, let's say, same color, but it has a different orientation. So you have to see that the thing that was red is now, not in the orientation that it was earlier. So you're really sensitive to the conjunction of the 2 factor values, so the combined value. So here, this is just a rough sketch, and in the book there is a little bit more about that. So for instance, if you have this visual scene, you would create a working memory representation of the scene that will show up here on the left as scene working memory. That's over a color space field and a orientation space field. The orientation, the feature along this row is always the same. It's always color here, and it's always orientation here. So you would create that by intentionally selecting one item at a time, any of these objects. So here the most salient one was maybe on the left. So you're selecting that spatial location. That makes that the peaks at this location, which are for red and for that particular diagonal, are activated, and they create these inputs into these fields. These are 3 fields over just the orientation dimension here, just the color dimension. They have played different roles that I'm not explaining in detail. And at the same time, you're providing information about the location that you selected through this shared spatial dimension that all the fields have. And that gives you this ridge. Now combine these 2 ridges, have an input there, and this is actually a copy of what happens here. This field here is a field that has a single peak. Global inhibition can only create a single peak at a time. This is one that can create multiple peaks as working memory. So when you have this localized peak, then you're creating a working memory version of that. So that's how you bring in the first item. Do the same for the second item by selecting this. And there's actually some mechanism in this field through inhibition of return that after you did the first one, then the next one will come up. And the sequential organization is not something I have explained here. And through that, you're now assembling, let's say, the green vertical, and then entering that. And this is after actually the item on the right has already been entered. So that's how this came about. And you see here that, so this is after this was done. And you see here now that you have these 3 transform these items from the scene separately, item by item, but separately into this color field versus spatial field, but they are aligned because they all share the spatial location. And you can see the binding problem can arise here as well. And that's why you have to do it one item at a time. And that's one of the features that you compare to experiment, where you find that there is that attentional bottleneck. They can only commit items to working memory that you have actually attended. And you attend one at a time. And then you can ask these change questions, which I'm going to skip here because I didn't explain change detection. I actually had a little slide about change detection, I believe, 1 or 2 lectures back. I don't remember exactly. Maybe you can retrieve that. So you can maybe imagine in principle how change detection would work once you have this working memory representation. Now, this means that we have that attentional bottleneck. So that's interesting because that's experimentally real and we kind of see where it comes from. It's also interesting in that it actually now opens another chapter, and then this will be, will be the last point I'll now be reviewing in a moment. In terms of coordinate transform, because the way we're assembling here this memory can be informed by some spatial coordinate of the object, but it doesn't have to be the retinal space. So for instance, in many cases, you would be selectively attending to this object by looking at it. So it will be foveated. So in your fovea, this will be at central location. And when you later do this for this object, that will be the fovea location, and that object will be the fovea location. So you have a problem if you want to represent in working memory these items. The spatial location is always the same. It's always the fovea, but of course your eye was looking at different locations. So what you actually want to do is you want to store the scene in a frame that is anchored to, for instance, the scene or to your body or to some other frame. And you have to have some mechanism of how to know where your fovea is looking. So when you're selecting this, what spatial location in your retinal space corresponds to what allocentric location, out, let's say, in the frame anchored to the world. And I'll explain next how that's done through a coordinate transform. And let's say, given that that can be done, then you can assemble this scene memory in a different reference frame than the one that you have to immediately sensorially accessible. That's an important feature of doing it one item at a time. And I will be explaining this in a moment. And the important thing is the spatial, the transformation of space actually only is about space. You only need to know about space, and we'll see that requires a certain number of dimensions. So we don't need to transport all of these features. Let's assume you have, your 15 different feature fields. So you have these 15 different fields that tune for different feature dimensions, and would have to directly transform all of those, and we would have to have the machinery that connects each of those to the corresponding representation over this different space. And there will be an awful lot of transformations that are very costly, as you will see. And we don't need that because because all the items share space. So because there's only one spatial representation, it's enough to know how spatial locations are remapped. And then through this machinery, we can transport the feature information across, as long as we do it one at a time. And we don't have to find out a way to transform each individual feature field into a new reference frame. So that's an important property of this form of binding through space, that it's also enables transformation across space. So this is the core binding mechanism for which there's ample evidence in the psychophysical literature, and there is a little bit of evidence for the coordinate transform, which I'll come to. So that's probably very real, neurally real. There are similar ideas in audition, where it's also actually auditory space, which is not as obvious as retinal space. Auditory space is important for combining different feature dimensions. There are a lot of phenomena of that nature, where you construct auditory space by binaural difference and by some kind of way of estimating the elevation of a sound source. And again, there are attentional deficits. It's also sometimes something called streaming, where you're paying attention to a particular stream of auditory events, and you do very similar things. In our current work, we're actually generalizing this idea that there could be also other kinds of binding agents, as we call about that. You don't always have to have space. You can also bind through something like an identity, something like a label or an index for categorical objects. And in the new year, there will be one lecture by Daniel Sabinas, who's running the exercises, and he will be talking about work that assists PhD thesis actually on that generalizes this to an index dimension. We'll see how deep he can go, but he'll at least hint a little bit at that. Good. So this last thing that I wanted to review is coordinate transforms. It turns out it's mathematically analogous to what we just looked at, particular form of transforming high dimension information. So what are coordinate transforms? Now, this is a little bit misunderstanding sometimes, in physics and other disciplines. Coordinates are what we scientists use to represent information, and you can actually represent information in different coordinate frames, and the information shouldn't really depend on that. So I'll be more specific here to show you what is really meant by it. So let's say a very simple kind of idea would be that your visual array, you have an object, and you might want to reach it, and you want to be able to reach for it if you're looking at it, but also if you're looking somewhere else, let's say, maybe even, you don't have to exactly look at it. It's only under one condition that you can do that. And that would mean that the visual information that differs in these different cases has to be transformed into a form that informs the arm about how to reach to the object. And that will be the example that I will be going through in more detail. But similar things occur everywhere. So, for instance, once you know where in the visual array, let's say on a table, an object is they want to reach, you also actually have to transform it into a form that is centered in your initial position of your hand, because only then you can actually know in which direction and to which extent and how far you want to move your hand, right? The information about where something's in the relative to your body isn't yet sufficient. It's sort of like varying where the hand is initially. is an analogous problem. And there are many other instances of this. One can even talk about this in a purely mental way. For instance, you could think of mental arithmetic of being a problem like that, where you have maybe some neural structure to add something. And when you're add to a particular number, you have to apply that neural structure at different locations along your number representation. I had alluded earlier to a number line, and you would be operating at different points of the number line. And so what you actually need to do is transform the representation of the number or of your operation. You can do either, so that it now can be applied to a different number along that line. So the example I'm going through is this example where we have a discrepancy between the retinal image and then the visual representation that enables some action. So I'm actually not making a difference between eye movement and head movement, assuming that they are both, that's fixed. I'm talking about transformation to body-centered frame. So for instance, when you're looking here at the scene, and this is the orientation of your eye, or your, combined with your head, then perhaps the red item is in the center of your fovea, and that's what you'll be seeing. And if your body has not moved, so the eye is still at the same location, but you're just rotating your head and your eye and looking at this object, then on the retinal array, on the visual image, or on the camera frame, if you wish, the image has changed, right? Now the green is in the center of that image, and the red is to the left of that. So your visual image will change, but your physical configuration hasn't changed. So if you want to act in that world, you want to transform, for instance, this image into a representation that is the same as it was in response to that first image. And what that means is transformation from retinal to body space is that you want to have a mapping from retinal to body space, but a mapping that depends on where you're looking. Neural networks are perfect for mapping, right? The projection from one set of neurons to another other set of neurons that can do any transformation, any shift or rotation or any transformation. That's what neural networks are very good at. But here we don't have a fixed transformation like that. We have a transformation that depends on something, namely on where you are looking. So we sometimes call this a steered transformation. And that is actually much more costly, because you'll see in a moment that means that you have to have projections for all possible values of this steering dimension, namely for all possible gaze angles here in this case. So it's a lot more cables, more neurons than needed if you were to just make one projection from retinal space to body space. So you see that there is what you actually need is an anatomical binding, and this is what is actually called a gain field, a binding where you're representing every combination of the space you want to project from, retinal space, that will be this dimension, with every possible value of that steering dimension, the gaze angle. So I'm plotting this along with this dimension. So any location here represents a particular combination of gaze angle and retinal location. There will be a bound representation, anatomically bound. And now any such location uniquely specifies where the object that caused activation here is in the body frame. And I'll illustrate that by going through a few examples for you now. I'll just mention that there is some empirical evidence that these kinds of maps exist. This goes back to someone called Anderson working in California, and a theoretician called Bouget, who generalized these ideas and showed that this can do coordinate transforms. So they find signals for that in the sense that neurons in the parietal cortex, LIP, is a particular area in parietal cortex, are spatially tuned, so along this dimension, and then the tuning amplitude depends on the gaze angle. So it's like a gain factor. You're amplifying the tuning curve or reducing. You could see if this ridge here goes through the tuning curve for space, you have a large tuning curve. So the gain will be large, and if it doesn't go through, you have a small tuning curve, and that's what's empirically observed. So it's consistent with what would be happening in this field. Now let's look at a couple of situations to get a sense for why and how this works. So here this is from Sebastian Schneegantz's chapter in the book. So here's participant looking straight. There's a visual object a little bit to the right. So gaze angle is 0. The stimulus is at 10 degrees retinal, and it's also at 10 degrees body-centered. And so in this bound representation, we have 10 degrees retinal input. It's a ridge. And you have 0 gaze angle, a ridge, and where they intersect, that's the 2D representation of retinal space and gaze angle. So this is a very good example where you see that the information you have about the high-dimensional representation is really combined, actively bound from separate information, because the information you have about your gaze angle comes from, maybe differentioscopy or some proprioceptive information about your muscles in the eye, or also the neck muscles and so on. There's a lot of work about how we can estimate where we're looking. And that is not a priori connected to the information you have about the retinal array, and which would be the visual pathway. And so combining these two takes this kind of process. Now, if you project out of there, let's not get to that. So here we've just shifted the participants looking at the object. So the stimulus is now in the retinal frame at 0. The gaze has changed to be 10 degrees, and the stimulus has not moved relative to the body. It's still at 10 degrees. So this has shifted here to the left, and this has shifted up. So you now have this location. It's still the same location in the auto frame. And do this for another gaze angle. And you will find, if you do this a couple of times, that all the possible combinations of retinal location and gaze field lie on this line, as long as the object is in the same spatial location. So actually this line here is specific to their spatial location. If you think through that, you will find that if you project out along the diagonal, then and you vary where you do that, then you actually sample the body-centered position. So if you're looking, for instance, at a line further up here, that would be a position further to the right, the retinal angle will be larger given everything else is constant, or you would have to move your eye more to the right to see this more in the center of the receptive field of the retina. And so that maybe makes sense that this is how you get that. That it's exactly straight line and so on. That is because we made this very simple model of adding these angles, but it could be some complicated functional curves. It's something that neural networks are very good at learning. And actually, we did a project on learning such coordinate transforms in the past. US and Demiska did that in her group in Bochum. Okay. That's how that works. And so this is the result. And then very typically, we're actually thinking that these kind of maps would be bidirectionally coupled. So you can not only take retinal information and gaze information to compute where something's on the body, but you could also use information about where something is relative to your body. For instance, some object you have in your hand, and know where you're looking and predict then where that object is on the retina. I'm predicting where to look at your hand would be the simplest case. And in fact, there is some interesting empirical information here. First, a little illustration of that. So here is a retinal input. It was actually on here a moment ago. The blue line is retinal input, and the red line is actually what is predicted from this model, which I'll explain in a moment. So see two inputs here, two ridges that are combined with my gaze angle at just one, where they intersect, the peak is formed, and then that projects out here into the spatial array, which now initially, when you're looking straight ahead, is identical to the retinal array. And these peaks actually predict also, because the coupling is bidirectional, right? There is a diagonal input here, you see some misbindings. That predicts the retinal location. That's the red curve here. Here the prediction matches where the object is and doesn't do much. But then a little later in the simulation, the visual inputs are turned off now, And so now we only have the prediction, and this is in the sustained mode, so you still remember where the peak is, and you're predicting where it was or would be seen. And now there is a gaze shift. So we're, see this, we're shifting gaze, so we're shifting this peak, and as we shift the gaze, running here, gaze shift, and what happens is that now the intersection lies somewhere else, and there's a new prediction arising. Now, after the gaze shift, the object appears at a new location. That's what we predict. We applied this model to predict some or account for some really curious data. This is a whole set of data, but just a little highlight of that. There are actually in MRP, there are some cells that have tuning curves. This is where a monkey is fixating. This is where this particular neuron that we're looking at here has its receptive field. So if there's an object in that receptive field, the neuron fires. This is when the stimulus is on, the neuron fires. When the stimulus is turned off, the firing of the neuron goes down. So they're a little bit like working memory. But if the monkey actually moves the gaze away from that object in this direction, so there's nothing in the receptive field now by active movement, then it's actually actively cut off. In this case, actually, stimulus persisted, but there's an active cutoff of this activation. It's also interesting. And now the fancy thing is that when you briefly present an object here while the monkey is still looking here, this is different cells. So you see the receptive field is a bit different relative to this location. So this receptive field relative to this location. At this point, the stimulus did not fall into the receptive field, so the neuron is not really responding. But after the eye movement has occurred, the stimulus would have fallen into the receptive field of that particular neuron, but it was actually no longer on. But even so, there is activation induced into the neuron. So the neuron is reacting to a stimulus that it never sees in the receptive field, but that it predicts that it would see after the saccade. Now, after the saccade, there is actually no input there, so the input is shut off. There's information about the absence of that input. And so it is only a transient activation, and actually we model that with this mechanism precisely. So this is showing that there is this bidirectionality potentially going on in the brain, where you're using information about your gaze to predict where stuff is that you previously saw. So of course, this prediction is caused, of course, by some neurons that did fire in response to this input, right? We're only looking at one neuron here, but the other neurons that represent that, and the activation of those neurons is then used to transfer that activation. Okay, so coordinates is a huge field, of course, but coordinate transforms can be built with these high-dimensional fields using the bound representation of the steering angle, the angle or the variable that steers the transform with the representation in one of the frames, and it produces then a basis for predicting the frame. In reality, of course, visual space is two-dimensional. So the retinal-centric field is two-dimensional. The gaze is two-dimensional, right? And so you have a two-dimensional gaze field. So this bound field is four-dimensional. I'm illustrating that here by having little tiles, and each tile is a two-dimensional field, and then the overall tile, that makes the 4 dimensions, and that is then projecting onto a two-dimensional field for the body-centered. So it's costly, and and I previously argued that this is how you would transfer spatial information into body-centered, or when you do object-centered, you can use the same kind of ideas for our externally grounded reference frames, which we're using all the time. So this would be, again, if you have 100 neurons per dimension, then this would be 10 to the power of 8, 2 times 4. It's already, it's still costly, but doable. And you see, this is still so much cheaper than dragging along all the other dimensions. Imagine if you were to do this separately for every dimension, then now this would be a 3D field. No, the gaze field would be fine, but this field would have, let's say, color as a third dimension. So we add color to every one of those and then add color here. And then you have to have the same thing for, I don't know, orientation. And again, the 5-dimensional space for orientation, all of that would have to be reproduced, copied for orientation, and you get orientation versus space, and that for every feature dimension. So every feature dimension would have to have separately that machinery to transform. And the particular way we do the binding through space makes that unnecessary, because we can just use this one complex machinery for space, and then the feature can be transformed through this binding through space mechanism that we showed. And that is very nearly plausible. We do find, these gain fields that are consistent with this mechanism in parietal cortex, which we know is largely about space. And so it's the dorsal pathway that is spatial or intended to action. And that obviates the need to have machinery of that nature for instance, IT for the what pathway, where we have all these feature dimensions, information about objects. So this attentional bottleneck could also reflects binding, but it could be interacting or related to this fact that we're seeing the world in these frames, not retinal frames, in these frames that rest in the world. And to do that realistically, you really have to use this binding through space idea. So very interesting kind of direction. Yeah, so this ends this this is like this bridging lecture between DFT core concepts and higher cognition. This is how you can get to higher cognition. And specifically, I showed how binding and this binding through space, search, and coordinate transforms are made possible by high dimensional neural fields. And so I close this lecture today, and we'll be connecting then in a series of lectures to particular applications of these ideas in higher cognition. And sequence generation will be one important step to do there.